Solutions are homogeneous mixtures, and homogeneous mixtures are the type of mixtures where when you look at them, they look like a pure substance, and they can actually be separated using physical methods, because they are they have a physical attraction between the components in the solution, so you can actually use like distillation or evaporation to separate the components in a solution. A solution is made of two different components, not just two things, but two components. You have a solute and a solvent. The solute is what you're dissolving in your solution, and the solvent is what you're using to dissolve the solute. A solution can be in any of the three physical states. It can be a solid, a liquid, or a gas. You can have more than one solute, you can have more than one solvent. When the solvent is water, a solution is known as an aqueous solution because water is the solvent. Now, when a substance can be dissolved in another substance, you say that that substance is soluble. If a substance is not soluble or it cannot be dissolved in another substance, then it's insoluble. To refer to the solubility of liquids, we use the word miscible. So if you have a liquid and that liquid is actually soluble in another liquid, then your two liquids are miscible. For solids, the solubility of a solid is highly dependent on temperature. In general, increasing the temperature will increase the solubility of a solid in a liquid. For gases, the solubility of gases depends on two things, not just the temperature, but also the pressure. The relationship between solubility and temperature for gases, it's inversely proportional. Increasing the temperature of a solution containing a gas dissolved on it, it will make the gas less soluble. As you increase the temperature, the gas dissolved in, let's say, water, for example, as the solvent. The gas dissolved in water will gain kinetic energy, and that kinetic energy can be enough. Like if you keep increasing the temperature, it will reach that point where the energy is enough for the gas to escape the actual solvent or the water. For pressure, the relationship between pressure and solubility for a gas is directly proportional. Increasing the pressure will make a gas being like more soluble in a solvent, and decreasing the pressure will make your gas less soluble. Now I'm going to spend some time talking about the types of solute. Remember, in your solutions you have two types of components. You have your solute, which is what you're dissolving, and the solvent, which is what you're using to dissolve the solute. We have different types of solute. Your electrolytes are substances that when they are dissolved in, let's say, water as your solvent, and they are dissolved in water, they can conduct electricity. Your electrolytes, they can conduct electricity because you have actually ions in solution. So electrolytes, we have two groups. We have strong electrolytes and we have weak electrolytes. And for this part, I'm talking about electrolytes, thinking only about ionic compounds, but we will learn later that we have a specific type of compounds that are not ionic, that they can also act as electrolytes, and those are your acids and bases, which is a topic that we go over at some point before the semester ends. So for your electrolytes, we're going to look at specifically ionic compounds for this part. So your electrolytes, you have strong and weak, and that's going to depend on the degree of dissociation of your electrolyte in water. We're using water as the solvent. When you have a strong electrolyte, your strong electrolyte dissociates entirely. So if you have a strong electrolyte as a solid at room temperature and you put your strong electrolyte in water, your electrolyte is going to dissolve in the water, giving you only ions. And then on the other hand, we have your weak electrolytes. For your weak electrolytes, when you put a weak electrolyte in water, your weak electrolyte is going to dissociate into ions, but not entirely. Just a small part of your weak electrolyte will dissociate to give you ions in solution. And the majority of your weak electrolyte remains as a solid without dissolving. So I'm going to give you one example for each one. For strong electrolytes, sodium chloride, that's my example, sodium chloride. Sodium chloride is a soluble ionic compound, and when you put sodium chloride in water, what you have is your ions, only the ions in solution. Okay? So I'm writing AQ for each ion because they are in an aqueous solution if you're dissolving your sodium chloride in water. And then it's also important to look at what's happening right there. I have one arrow pointing towards the product side or towards the ions, because that's what's actually happening. Your solid is dissociated into ions in solution and you have only ions in solution. Then for your weak electrolytes, there's a partial dissociation, and we use a different type of representation for these ones here. So I'm giving you another example. For your weak electrolytes, we have a lot of the solid without dissociating, without going towards your ions, and then we have a few ions in solution. Your weak electrolytes are classified as insoluble. Even though part of them dissolve in water, that part, it's a small part. The majority of your weak electrolyte remains as a solid in water. And then we have the solubility rules right here. And the solubility rules will help you to determine which type of compound it's an electrolyte, strong or weak. All of them are actually electrolytes. You just use this one to determine if they are weak or strong electrolytes. So I have here the first half, and I'm going to show you like how to use your solubility rules. This half here, it's classified as soluble. So these compounds listed here, or the compounds that you get with the combination of these ions with a positive or a negative ion, will give you soluble compounds. So let's look at rule number 1 here. Elements from group 1, you have them listed there, but those are your metals from group 1 with positive charge, positive 1 charge for all of them. And ammonium, your polyatomic ion, the only polyatomic ion that you have listed with a positive charge. All of them are positive ions, so you can combine all of those positive ions with any negative ion. And the compound that you will get from the combination of any of these ions listed here in number 1 with any negative ion that you can think of, polyatomic ion or your nonmetals from the periodic table, will give you compounds that are always soluble in water. Something similar is happening here with your rule number 2. Nitrates, chlorate, perchlorates, and acetates, all polyatomic ions with charge of -1. You can combine them with any positive ion, any metal from the periodic table with a positive charge, and they will always give you soluble compounds. All of your soluble compounds are strong electrolytes. When you put them in water, you will get complete dissociation, and that solution is capable of conducting electricity. And then I want to go to number 3, and then I will show you just one example for the insoluble because it's the same thing. In number 3, you have listed chlorides, bromides, and iodides. Okay? All -1 charge, all in group 7, -1. So if you have chlorides, bromides, and iodides, you will have soluble compound, with the exception of when you have chlorides, bromides, and iodides combined with silver, lead, or mercury. Okay? So if you have AgCl, Ag is +1, Cl is -1, so silver chloride right there is the one that I gave you here in your example as a weak electrolyte. If you combine chloride with an element in group 1, group 2, your positive metals, they will be soluble, but when they are with silver, lead, or mercury, they will be classified as insoluble. That's why these 3 are listed under rule number 3. They are exceptions to rule number 3 only. Okay. And then let me show you the insoluble part. The ones that are classified as weak electrolytes are your insoluble ionic compounds. So I have here rule number 5, your carbonates, chromates, phosphates, and sulfides. They all negative polyatomic ions. All of them are classified as insoluble, but you have an exception right there for rule number 5. So your exceptions, metals from group 1 or ammonium, which is the same as rule number 1. Rule number 1, all of them are soluble. So here, if you have carbonate combined with, let's say, copper, which is a positive ion transition metal, iron, the same thing, positive ion transition metal, those are going to be insoluble carbonates. Okay? But if you have your carbonate combined with any of these exceptions, with potassium, with sodium, lithium, or any other element from group 1 or ammonium, those are going to be soluble. So here, hydroxides and sulfides, they are insoluble with the exception of these ones listed here. Those are going to be soluble. Okay? So the exceptions in this part of your rules are telling you which ones are soluble, and the exceptions in this half here, they're telling you which ones are insoluble. Okay, they are the exceptions to the soluble ones. So I'm going to use my solubility rules to show you just one example here. So I have sodium iodide, first one listed, and you're going to use your solubility rules to determine if it's a weak or a strong electrolyte. For you to determine if you have a weak or strong electrolyte, the first thing that you have to know if it's soluble or insoluble. Soluble electrolytes are strong electrolytes. Insoluble are your weak ones. Sodium is in group 1, and that's listed right there. Soluble, group 1, always are soluble. There's no exceptions to rule number 1. So sodium iodide should be marked as a strong electrolyte. Silver acetate, that's the last one. Silver acetate that I'm doing. You can find either, okay, or the silver or the acetate ion. If you check, you have acetates right here. C2H3O2 -1 combined with Ag+1, that's silver acetate right there. And your acetates are listed as soluble, always soluble. So if you have silver combined with acetate, you don't have any exception for acetates. That should be a soluble, and if it's soluble, it should be a strong electrolyte. And then besides having strong and weak electrolytes, we have non-electrolytes, and for now we're going to say that your non-electrolytes are covalent or molecular compounds. You don't get ions in solution because you don't have ionic compounds. And remember, this is not always true. We're going to learn about acids and bases later, And for acids and bases, we have electrolytes, even though we don't have ionic compounds. But for now, we're using covalent molecular compounds as non-electrolytes. So you don't get ions because you don't have ionic bonds in your covalent or molecular compounds. So your non-electrolytes or your covalent compounds, they are soluble in water. But when you dissolve a molecular compound in water, you're not getting ions, okay? So this here, it's methanol, it's an alcohol, and it is soluble in water. You have that OH polar bond, hydrogen bonds, it will make it soluble in water. But when that dissolves in water, you get only the molecules in water. You're not getting any ions, okay? Now I have here a summary about your types of solute and what you're going to have in solution for each one. If you have a strong electrolyte, you have only ions in solution. If you have a weak electrolyte, you have a mixture. You have just a few ions and the majority of your electrolyte without dissociated, with no dissociation in solution, mostly the solid, a few ions. And then your non-electrolyte, you don't have ions because your non-electrolytes, they are not ionic compounds, they are covalent compounds. Therefore, you have no ions in solution. So you will get only molecules. And here I have a representation. These are generic things. I'm using AB for a strong electrolyte, CD for a weak electrolyte, and then I have a non-electrolyte as EF. So if you have a strong electrolyte in water, you should have only ions. You see I have A plus, B minus, A plus, B minus, only ion because it's a strong electrolyte. Here I have two things. I have my ions and then I have CD, which is my actual compound right there. No dissociation to give you ions and some ions. That should be a representation for a weak electrolyte where you have both things, a few ions and also your compound without dissociation. And then the last one here should represent a non-electrolyte because you have in solution only the molecule EF, FF. You cannot see any ions in solution, so that's a generic representation of what you should have if you dissolve this non-electrolyte in water. You should have your molecules dissolved. You don't get to see the molecules, but there are no ions in solution. So this here, it's mostly definitions. We have types of solution based on how much solute you have in a specific amount of water. So we have three types of solutions. We have saturated solutions, unsaturated, and supersaturated. That's going to depend on temperature. So when you have a solution where you're dissolving the maximum amount of solute in a specific amount of solvent at a specific temperature, that will give you a saturated solution. So you don't need to know the solubilities. Okay? This here, that's information that I'm giving you so you can check which type of solution you have based on that solubility. You can find solubility in tables, in the textbook, or online. So I'm giving you that information. For potassium nitrate at 20 Celsius degrees, you have a solubility that is 24.2 grams of potassium nitrate in 100 grams of water. It means that a saturated solution for potassium nitrate, when the temperature is 20 Celsius degrees, for you to have a saturated solution, you need to dissolve 24.2 grams of potassium nitrate in 100 grams of water. Okay? That right there will give you your saturated solution. Then an unsaturated solution, it's a solution that contains less solute than that maximum amount that you can dissolve. Okay? For potassium nitrate at 20, the maximum amount is your 24.2 grams of potassium nitrate in 100 grams of water. So if you have less of that, less of 24.2 grams of potassium nitrate in 100 grams of water, you will get an unsaturated solution, because to that solution you can actually add more potassium nitrate, and your 100 grams of water should be able to dissolve additional solute. So in my example, I'm giving you 20 grams in 100 grams at the same temperature. So that will be an unsaturated solution, because at saturation you are going to have 24.2, so you can actually dissolve 4.2 grams of potassium nitrate in addition to your 20 to get to saturation. So this one here, it's unsaturated. You can still dissolve more of your solute. And then the last type here, it's supersaturated. Now, this one here contains more, okay? A higher amount of your solute in the same amount of the water. I'm giving you 30 grams in 100 grams of water at 20. Okay, so you know that at saturation you have 24.2 grams in 100 grams at 20. So if you have more of that, that will give you a supersaturated solution. Now, for you to do a supersaturated solution, you have to actually increase the temperature. If you increase the temperature, let's say to 30 Celsius degrees, now, since the solubility of your solids depends directly on temperature, increasing the temperature, increasing solubility, if you increase the temperature, you can dissolve more than your 24.2 grams of potassium nitrate. But if the temperature is higher than 20, you cannot compare that to your 20, because we're comparing solubility at a specific temperature. Okay, so if you heat your solution to 30 and you can dissolve, let's say, all the way to 30 grams of potassium nitrate, that solution is not supersaturated. Okay? If your temperature goes down from 30 to 20, yeah, the same temperature that we're using to compare these two here, you were able to dissolve 30 grams of potassium nitrate when you heat it up to 30. If your temperature goes down to 20 and you still have your 30 grams of potassium nitrate dissolved in your 100 grams of water, then you do have a supersaturated solution. Supersaturated solutions are not stable at all, because you have more solute than the actual amount that you should have for a saturated solution. Okay, so they're not stable. If you move them, if you make a slightly disturbance on your solution, your solid will come out of your solution, because you have more than that saturation point. And then I have here an example, and it's a very interesting example. I'm giving you solubility for sodium chloride at 50 Celsius degrees, and I'm telling you it's 38 grams in 100 grams of water. So 38 grams of sodium chloride in 100 grams of water will give you a saturated solution. That's the maximum amount of sodium chloride that you can dissolve in 100 grams of water at that specific temperature. If you check here, 35 in 100, 35 is smaller than 38. That will be an unsaturated solution. On the second one, you have 76 in 200 grams of water. If you check, if you have 38 in 100, in 200, you can actually have 76 grams. Okay? So this second one right here, it's also a saturated solution. Okay? you have twice as much of the solvent, twice as much of your solute. At the same temperature, that will give you a saturated solution. And then the last one, here you have 40 in 100, and the solubility for saturation is 38 in 100. So this one here should be a supersaturated solution, 40 in 100. And then I have here 3 problems for you to work on. You can ask me for the answers.